The MCP4131 is a digital potentiometer. There are quite a few videos about this device and digital potentiometers in general, so I'll not spend much time introducing it. Instead, this video will focus on how the MCP4131 uses SPI in an unusual bidirectional way. We will dive very deeply into how this works and proper usage of it. If this is too much detail for you, use the chapters below to skip to Usage Summary, after which we see how to use SPIDEV on a Raspberry Pi to support all of the MCP4131's features. See the link below if you need an introduction to digital pots. This diagram shows the MPC4131's pinout and how to connect it to a Raspberry Pi. P0A, P0W, and P0B are the potentiometer pins. The connections shown form a voltage divider, so if you measure the voltage between P0W and ground, you will get a value between 3.3 and 0 volts, depending on the pot's wiper position. The Raspberry Pi sends commands via a SPI bus to set the wiper position. There are commands to read and write the wiper position register or to increment or decrement its value. What's unusual is that the MPC4131 uses only a single pin called SDI-SDO for SPI. Normally, SPI uses two unidirectional pins. MOSI, which stands for Master Out, Slave In, carries data to the slave. MISO, which stands for Master In, Slave Out, carries data from the slave. There are also clock and chip select signals. The slave pays attention to the SPI bus only when its chip select is active. This allows multiple devices on a SPI bus. Connecting a single pin, SDI-SDO, to both MOSI and MISO is kind of weird. How does it work? And what does the resistor do? Do you need it? What value is appropriate? Does the master have to do anything special to make this scheme work? Short answer, the resistor is a good idea even if you only write to the MCP4131. For 3.3 volt systems, a resistor value of around 2.2K but less than 10K looks good. Let's dive deeper, since one might be tempted to copy the MCP4131 SPI design in an FPGA project. To begin, here's a scope capture of the Raspberry Pi reading the wiper position register. SDI-SDO is the yellow trace, chip select is magenta, and the clock is cyan. Focus on SDI-SDO. The Pi drives the first 6 bits, 4 bits of register address, and a 2-bit command. The address is 0, and the read command is binary 1-1. The bits driven by the Pi are annotated in red. But then, the MCP4131 starts driving. It responds to the read with a command error bit with value 1 indicating no error, and then the value 5, which is the current wiper position. The bits driven by the MCP4131 are annotated in orange. This is a bit magical, given that the Pi's MOSI output is push-pull, not open-drain. It never really stops driving. This diagram is from the MCP4131 datasheet. It clearly shows that SDI-SDO is an open-drain output with what Microchip calls a smart pull-up. Notice the control logic. The open-drain transistor can only be turned on when the MCP4131 needs it to be. That is when it's driving the value of a bit. The smart pull-up is also active at this time. If the Pi's MOSI output were also open-drain, this would be a normal bidirectional open-drain connection. There would be a pull-up that has no need to be smart. But SPI MOSI is not open-drain. Here's my model of what's going on. The red oval shows a typical push-pull output for MOSI. There are 2 transistors. Only one of them is switched on at a time. The top transistor is on when the Pi drives MOSI high. The bottom transistor is on for low. The blue shows roughly what I think the MPC4131 is doing. The top transistor makes the pull-up R2 smart. When the top transistor is on, the pull-up is in the circuit. This transistor is definitely on when the MCP4131 is driving an output bit, but it can also be on at other times. The bottom transistor is a conventional open-drain setup, but this open-drain transistor is on only when 2 things are both true. The MPC4131 is driving an output bit, and the value of that bit is 0. Note that the inputs labeled 2 MOSI and 2 SDI are high impedance. They never materially affect the circuit. Now, let's consider a case in which the Pi is driving low, the MCP4131 is not driving an output bit, but its smart pull-up is somehow enabled. We're assuming the pot is not outputting a bit, so this transistor is off. But what if this transistor is on? And the Raspberry Pi is outputting a low. So that would mean that this transistor's on and this transistor's on, and we'd have a current path from VDD through this resistor, through here, through this resistor, and then to ground. So the two resistors together would be forming a voltage divider, and we'd expect to see an intermediate voltage here, which would not be good. Let's look at some scope captures. R1 is 22K. Look at the yellow STI-SDO trace. It's a mess. The Pi can't consistently drive STI-SDO lower than about 1.6 volts. Some low bits are okay and others are not. It looks like the smart pull-up is indeed sometimes enabled and has a value of roughly 22K. That's lower than my guess of 40K. An R1 value of 15K is still bad, but the Pi manages to pull the signal a little lower. With an R1 value of 10K, it looks like the smart pull-up is disabled for all low bits. It's like the Pi is pulling low hard enough that the MCP4131 agrees to get out of the way all of the time. Its datasheet suggests that it does something like this, but the waveform still does not look great. Here's a capture with an R1 value of 2.2K. It looks good for our 3.3 volt system. Let's conclude that R1 should be well under 10K when the Pi is driving low and the MCP4131 is not driving at all. But do we really need R1? Let's move on to the next case. Things get interesting when CTL is high because the MCP4131 is trying to drive a value to the Pi's MISO input. What can happen if this resistor isn't present? Well, we'd have a high current path from VDD through this transistor, across here, and then down through this transistor. The current could be high enough that it could damage this transistor or this transistor. Now, this can only happen when the Raspberry Pi is driving high and the digital pot is trying to drive low. So it can only happen when the digital pot is trying to do an output. Could we avoid this problem by having a software rule that says that during any bit where the digital potentiometer is trying to output, we require that the Raspberry Pi drive low? Well, no, that doesn't work because it brings back our voltage divider problem. So we'd have this path here whenever the digital potentiometer is trying to output a high. So in fact, we have to have a software convention that the Raspberry Pi must drive high on every bit in which the digital potentiometer is trying to drive an output. Otherwise, outputs don't work when the value is high. And we can see that with scope captures. In this capture, the Raspberry Pi drives low during the last bit of the read. The correct value of the bit the MCP4131 is outputting is high, but we see an intermediate value near low instead. This is the voltage divider problem. The Pi must drive high during all MCP4131 output bits. It does so in this capture, so the value read is correct. The value is 7, the last bit is high, and all is well. In summary, the Raspberry Pi must drive a high value during every bit that the MCP4131 outputs. Use resistor R1 to prevent high current when reading zeros from the MCP4131. A value of 2.2K is good, but stay well below 10K. And keep in mind that every MCP4131 command can output. The command error bit is an output, and errors are indicated by zeros, including in every bit following command error. Next, we can look at the MCP4131 in action and take a quick look at SPIDEV software on the Raspberry Pi. Here's our test setup on a breadboard. You can see the resistor. I'm using a Raspberry Pi Zero. We can just SSH to it and build software natively. So here's the system running. We have a terminal window on a Raspberry Pi Zero on top, and then a scope capture showing the voltage level of the output voltage divider on the bottom. So that will show a signal between 0 and 3.3 volts. And on the Raspberry Pi, we have a program that drives the MCP4131. I can build it like that and then run it like this. And when I type HE, it shows a list of commands, which include the 4 commands that the digital potentiometer supports. So the potentiometer has some registers. Register 0 is the wiper position. So you can read and write registers, and you can also increment and decrement the value of the wiper position. So let's demonstrate reading and writing first. So if I do a WR to register 0 of hex 80, that causes the wiper position to be on top and gives a 3.3 volt output. Then I can read 0 and see hex 80 is the last bit. It's actually showing all of the bits. It's a 16-bit command, and so it's showing all 16 bits that the Raspberry Pi reads when it does the command. So the last byte is the value of register 0. So let's do a WR to 0 of hex 40, and it should give an intermediate level. And I can read that back, and we see 40. I also have commands to increment and decrement. So right now it's reading 40. So if I do IN, which is an 8-bit command actually, and then another read, we see that it went up 1. So I could do two more. I'll do 2 more if I can type them properly. Do an RD0, and we're up to 43. DE is decrement. So read 0, and we can see that it decremented. And then also I implemented a couple of commands to basically make a triangular pattern by incrementing and decrementing. So I can do a command that does that 100 times, and we can see a triangle wave from that. And that's done with increment and decrement. TW does the same thing with writes. So we can see that. There are registers other than 0 that you can read and write. In fact, many of these digital potentiometers are dual pots. And interestingly enough, even though this is a single pot, the wiper register for the second pot is present, so you can read and write it if you want to. So for example, I can write to 1, say a 2, 3, and read 1. Doesn't do anything, but it works. And then also register 5, I think it is the TCON register. So if I read it, I should see, I guess maybe it's register 4. Yeah, I think it's register 4. So if I read it, I see a value of FF. And what this does is it controls whether or not pins P0A, P0B, and the wiper P0W are connected. And so I can disconnect pins. So let's do a write to 0 of an intermediate value. So we see that in the oscilloscope. And now I'm going to try to disconnect P0A, which should cause the voltage to drop to 0. So I do that by writing 4 and then FB. I think it's bit 3 that does it. So you see it went to 0. And now if I write 4 of FF, it should come back to its old position. And so those are the capabilities of the MCP4131. Next, we should look at some software. The ST command exits the program, and we see that the software that we've been running is just a single C file. So let's take a quick look at it. I won't go through this in complete detail. I'll put the software on GitHub and put a link to it below so you can review it. But down here we see that the SPIDEV that we have to open is /dev/SPIDEV 0.0. That corresponds to chip select 0. And by the way, SPIDEV is a user space library with kernel support that lets you write programs that run in user space on the Raspberry Pi to do SPI. So that's what we're using, is SPIDEV. And the MCP4131 actually supports faster write speeds than it does read speeds. So here I'm setting the write speed to 2 megahertz, which is actually a little higher than 3.3 volts might support, but it seems to work. You can read the datasheet about that. 1 megahertz would be a safer speed. And then the read speed is 250 kilohertz. And then, as we saw earlier, there are commands. Like, so when you do a SPI write to do a command, you first do 4 bits of register address and then 2 bits of command. And so these are the 4 commands that are supported and the 2-bit pattern that selects the given command. So now let's drop below to the main program. And you can see that the first thing you have to do is just open the SPI device. So you call open to do that. And that's a global variable, SPI-FD. And so now let's go back up to the top and let's drop down a little bit. And let's look at one of these, like let's do read. So to read the pot, reads and writes are 16-bit commands. And so I have a function called 2-byte command that does either a read or a write. So to do a read, you pass in the code for command read. To do a write, you pass in the code for command write. And then increment and decrement are 1-byte commands, 8-bit commands, and so they're similar looking. So the real action is in these commands, 1-byte command and 2-byte commands. So let's go up to one of them. Let's see, that should be 2-byte command here. So this is taking as its parameters the register address, so 0 for the wiper register, the command, from those command codes that we saw above, and then in the case of a write, the data to write, 1 byte of data. And so what you have to do is to form 16 bits to write. And so you do that by using this little character array. So the first byte is going to be the 4 address bits, shifted 4, and then the 2 command bits. And then this is kind of interesting here. Remember that every bit that the MCP4131 outputs has to be written as a 1. So for reads, the lower 2 bits of this register need to be 1s, and for writes, the command error bit does. And then the next byte is just the data to write for a write, and has to be FF for data to read, because again, we have to drive 1s whenever the MCP41 is going to output. So then after that, there's a structure that represents a SPI transfer, so that's part of the API to this. So you allocate one of those, you clear it to 0, and then you set the RX and the TX buffers, the length of the transaction, which is 2 bytes in this case, the speed, and the number of bits per word, and so on. And then this ioctl call actually does the SPI transaction. And so when that returns, the RX buffers are filled with what the Raspberry Pi sampled for the bits coming from the MCP4131. And so it's pretty easy to do. That's how you do a SPI transaction. And just briefly, we can scroll up and look at the one that's for a single byte command. So the only difference is you only have 1 byte to fill out, and then 1 byte to return. Otherwise, it's identical. So that's how this software works. And again, I'll put it on GitHub with a link below so you can take a look at it at your leisure. And the necessary connections, we saw them earlier in the presentation. So I think I'll end this video here. Hope you found it interesting. Thanks for watching.